And notice I've got a terminal here, got a little drawing pad here. I'll jump over to that drawing pad here and there. Yeah, today is our first stats day. And what does that mean? It really just means we're going to do a lot of Python, and we're going to focus it around stats problems. And the idea here is there's a statistics concept that is going to be looked at, focused on, and we're going to write Python around that. And today is going to be sort of like our warm-up day for future classes. I'm sorry, my cat's meowing at the door. 1 second. Okay, sorry about that. Today is sort of a warm-up day, and we're going to be coding some simple functions. Logic won't be that complex, and this is getting us, moving us in the direction of doing some more complex things later on. I'll cover a couple conceptual things here today, and let's just look at what we'll be covering specifically. And the way I generally do this is I'll just grab a slide and I'll bring it up into this space. So, we'll very briefly touch on the why of statistics. And today's focus is going to be on measures of centrality. So when we're talking basic statistics, often we're talking centrality and we're talking spread. And today we're focusing on centrality. And next stats class, we'll focus on measures of spread. And after that, we're going to look at some ideas in regards to sampling. We're not going to go deeply into sampling, but we are going to use it a lot throughout the remainder of this course. It turns out that, well, from our perspectives, there are three ways that we will generally approach solving problems. Okay, one is going to be through a counting approach. One is going to be through a sampling approach. And then one is through what I'm going to call a closed formula approach, where we actually have a formula or we have an algorithm, a specific algorithm, and we're coding that out either way. But counting and sampling, these two things might be sort of new to a lot of people. And, they sound easy enough, they sound simple enough, and they are, but we're going to kind of deepen those ideas. So we'll probably wrap up, just with a brief discussion of continuous versus discrete data. Those are important to understand, but we're not going to dive too far down a rabbit hole with that. Ultimately, we're going to be talking about discrete distributions and continuous distributions with much more focus on discrete distributions, but that won't be for another. That won't be until the last week. Okay. So, just as a starting point, let's think about why probability and statistics are important. So if you think about what data science is and where data science comes from, it is an emergent field in the last, 15 plus a couple years, where computer science and statistics have converged. And it's not just computer science and statistics, it's also the social sciences, right? There are a lot of practices in the social sciences that leverage machine learning concepts. And, such as, let's see, there's a famous couples counselor who really pushed, applications of regression within, prediction of relationship success, for example, through, 30 years of study. Ultimately, the abstraction of those kinds of practices looks like data science. Also, genetics really pushed data science in the late 90s, early 2000s with the genome projects. We get this emergent field of data science as a convergence and an abstraction of all these other fields. And if you're a data scientist, you go into situations maybe not understanding the domain the way somebody in a bioengineer might, right? You may not understand the domain itself, but you do understand procedures of approaching and synthesizing and modeling data. And you have to be very critical. You have to understand where your domain knowledge fits in, and you need to learn a lot of new domain knowledge for whatever you're working with. An example for me would be I was hired by a company that produces video products for lacrosse teams, and I didn't know anything about lacrosse, but I was hired to, model auto tagging of video for that company, right? So that they could in real time have video for these coaches where they could just scroll back to a tag, that one team scored over another. And I don't know how to play lacrosse. I still don't. I don't know much about lacrosse, but I could tell you a lot about it from my domain expertise in relation to the data of lacrosse. And so, when we're thinking about what data science is, it is an abstraction of a lot of fields. However, it is heavily, heavily informed by statistical concepts, by statistical understanding of, fundamental statistics and, the foundational kind of inferential statistics and Bayesian statistics. Like all of these things sit inside our algorithms and models and become very informative, very important to understand. Probability, well, everything, we approach everything as being some kind of stochastic process, right? Something's going to happen or it's not, or there's going to be some range of possibilities of a specific event. And we have to understand that. We have to think about it. And we kind of have to undermine our sort of incorrect intuitions about probabilistic concepts. And we need to have effective procedures to approach understanding probabilities. We'll talk about that a little more later on when we get into counting, because counting is a really good foundational way to understand probability. Most things in data science are rooted in prob stats somewhere. Although I wouldn't say everything, right? Biostatistics, which, is maybe, is focused heavily on statistics, but focused pretty heavily on biology. A lot of data science, I think, comes directly out of biostats. So, we don't want to just pin it on a couple fields, but we want to see it as the evolution of the sciences in general into some abstract thing that can sit on top of the sciences, informing modeling, experimental design, and critical thought in general. So I have a little comic here that I think this will be funnier. This will be funnier later when you get more into machine learning and artificial intelligence. So, we've got this crack on the wall, and it gets framed. We call it machine learning, and then we call it artificial intelligence for a crowd. And when you hear people talk about this space in like in media and things, like they're like artificial intelligence, and we get this idea of Terminator, and we get all these things that sort of strike fear into some people's hearts and excitement into other people's minds, and it's artificial intelligence. Well, what does that mean? Well, when you're out getting a job, often you're talking about machine learning. That's what you're doing. You are discussing algorithms that you've used. You're being in a technical interview, you're being assessed on your understanding of algorithms or your ability to implement them or choose reasonable algorithms to approach solutions to certain problems. And when you're actually doing the work, you're not thinking about, machine learning in general. You're thinking about the specific algorithm, whether it's logistic regression or a random forest, whatever that might be. So what we're going to cover today is going to be measures of central tendency, right? Or measures of centrality. And for us, that is, we're going to keep it pretty simple. We're going to limit it to mean, median, and mode. And next time, we're going to get into measures of variance or spread. And mostly we'll talk about variance and standard deviation, but we're going to talk about a couple others as well. We're going to talk about the interquartile range related to the 5-number summary. We're going to talk about, kind of systematic ways, classic systematic ways to remove outliers and things like that. But that'll be for next time. And what we're going to cover today is mean, median, mode. At this point, with your level of Python, if you were starting from scratch and you've done Python for the last 2 weeks, you've encountered all the things that you need to be able to code mean, median, and mode functions, except maybe a couple methods. And I'll probably check in on those, or I'll just cover them really quickly as we get to them. I think like the count method, I don't know if you've encountered that yet, but it's really simple. It just counts things in a list or some kind of collection. And we'll utilize that at some point, but you should have all the other tools. And we're going to be thinking about the logic and application of these measures of central tendency and kind of how to think about them and how not to overthink them. All right. So let's start with the mean. And unfortunately, I have a little bit of, there's a little bit of broken text in here where it says undefined control sequence, but let's not worry about that. We can ignore that. Okay, so the mean is just the sum of all the elements in a collection, right, in a list, divided by the number of elements. And the way we can express this, and I'll write this out and talk us through it, is through this mathematical formulation. This is just 1 over the number of elements multiplied by the sum. That's what this big E is, this sigma, capital sigma, the sum of each element, where we think of the elements in terms of their indices, right? So in the mathematical representation, we tend to start at 1. We go up to n, where n is the length of that list. And each element here we're calling A sub I, is going to be the ith element. So A sub 1 would be the first element, A sub 2 would be the second element. And I just want to point out that this is different from how we represent this in Python in terms of indexing, right? Where the first element is the 0 index. In the mathematical representation, we tend to say that the first element is the index 1 element. We've got a couple symbols here, and that all represent the mean. We've got lowercase mu, that's this sort of U shape here, and that refers to a population mean, and we've got x bar, which refers to a sample mean. So this brings up a number of questions, right? We need to think about what a sample is versus a population. So I'm gonna go ahead and talk us through this formulation again. We're talking about the mean, right? And we represent the mean in one of 2 ways. We've got the population mean, I should say population, and we've got the sample mean. And the population mean we represent as mu, right? The sort of U with a tail on the front. And the sample mean we represent as x bar. The way that we calculate the mean is going to be the same whether it's a population or a sample, okay? So that's just going to be, well, let's concretize this. Let's put this into a specific example. Let's say we have 1, 3, and 5, okay? This is our collection. We'll just do that, 1, 3, and 5. All right, so what we're going to do is we're going to take the first, add it to the second, add it to the third, right? We're going to sum all of those. So we're going to sum each value from the first value to the last value. And here we're saying that 1 is the first index, 3 is the second index, 5 is the third index, right? So we're going to sum all of those. Each of those can be represented by A, right? A sub I. So A sub 1 is going to be 1, A sub 2 is going to be 3, A sub 3 is going to be 5, okay? So what this breaks out to is going to be 1 plus 3 plus 5. And to finish calculating the mean, we're going to divide this by the number of elements, 1 over n, right? So in this case, this is going to be over 3. And we can see that this is 9 over 3, or 3, and our mean is here. Our mean is 3. That may seem obvious, right? That looks very central in our data, right? We can, it's 1 is 2 away from 3, 5 is 2 away from 3. It's an easy conclusion that this would be our central value. So let's think about what is meant by population versus population versus sample. You know what? I'll just erase that whole thing. So we've got population. Keep that in color black. We've got population versus sample. And the way that I'm going to illustrate this is, let's say we have a phenomenon out there. I like thinking about heights of trees in a forest. So there's some forest, and let's say we know perfectly the bounds of this forest, right? So here's that forest. If we're talking about a population, we're going to measure the heights of trees of everything in this forest, right? Everything. So if we get the population mean, that is going to be however millions of trees, all of their heights, summed together, divided by however many trees there actually are, right? And that's going to get us our mu, or our population mean. If it's a sample, we're going to think about this a bit differently. If it's a sample, we're going to grab trees from all over this at different points, right? Maybe we're going to get 1,000 trees. We're going to sample 1,000 trees randomly. We want the sample to be as representative as possible of all the trees in this population of trees. But there's going to be error in there. We're not going to be able to get the exact mean of the trees. And so we don't represent that with mu anymore. We represent it with x bar. So x bar represents the sampled mean, right? The sample mean from a representative sample from this population. Now, maybe this goes without saying, but our obvious goal is to make x bar look as much like mu as we can. We want x bar to be as close to mu as possible. That is a goal that we have. Whether or not we achieve that is going to be dependent on how we sample. And, there's always going to be room for error. There always has to be. And you might be thinking, well, are there any phenomena where we're actually dealing with a population and not a sample? Sure, there are. Like, let's say we have a classroom and we want to know what is the mean height of everyone in the classroom, right? We can ask that question and we can get a population mean for that closed space. We have limited the domain that we're analyzing. However, most of the time in statistics, we are going to be dealing with samples. We're going to be dealing, or in the sciences in general, right? Anytime you perform an experiment, you're sampling out of the ether, so to speak, right? You are getting a sample of all potential outcomes. And the more you do that and repeat that operation, of course, the more, the less uncertainty you have and the more surety you have. We have means of measuring uncertainty, and we do that. That's not something we're going to cover extensively, or we're going to touch on in this class. We're not really going to cover it deeply. But I just want to point out that most of the time we are going to be dealing with samples. We're going to default to thinking in terms of samples. So there's a concept that, that I'm going to have you think about in terms of the mean. And maybe I'll illustrate this with a list of numbers. So let's say we have 1, 3, 9, 12, and 2000. If we calculate the mean of this, what is this? This is for 13, 25. So this is 2025 divided by 1, 2, 3, 4, 5 by 5. So this is 405. So we have a mean here of 405. And I'm assuming we're thinking about this in terms of samples. If we have a mean of 405, and we look at our data, you might ask, well, is this mean representative of the data? I don't know, probably not. Maybe it is, probably not though. We can't see the originating data set necessarily, but let's just think, well, maybe this 2000 is not, it's some sort of anomaly. Maybe it's some outlier. One of the ways that we can rectify this is we can trim the mean. So we have this concept of a trimmed mean. A trimmed mean where, well, we just cut off the low and the high value. And now we can say, well, 3 plus 9 plus 12 divided by 3, well, that's just 24 divided by 3, which is 8. And 8 actually looks a lot more representative of this data, right? We want to be careful doing these kinds of things. We want to be careful anytime we're dropping data. But I'm explaining the trimmed mean here because I'm going to have you code a mean function in just a moment. And one of the optional parts of that is coding a trimmed mean along with that. So I'm going to be working out of, well, let's see. I'm going to navigate to source, stats, and let's look at the summary stats. And I'm going to just open this in VS Code, and I'll work out of VS Code here. Okay. Okay. Sorry, my computer is running a little bit slow. I'm going to try to close out a bunch of things while you're coding. Generally, my computer does not run this slow. So. Okay. So let me give you the breakout. Okay, so I'm going to have you code a mean function, and you can potentially include a trim parameter to remove the greatest and least n values. So let me show you what this might look like. Just a little bit of starter code, which I will also put in the Slack. So apologies. I think it's actually my because I record this locally. Maybe I'll just stop recording it locally and work off the cloud recording. See if that speeds us up. Huh. Okay. All right, so we'll call this def mean, and we're going to pass in a list, and then we can trim by some number of values. If trim by is set to 1, we're going to drop the lowest and highest values. This is optional, by the way. If you want to code this just on a list, def mean of list, that's fine as well. So I'll drop that in the Slack. And also this list of this list A, which is conveniently in order, but don't trust that it will be in order when we test the function. Okay, so I'm going to set a 5-minute timer, 4-minute timer. Go ahead and code that up. If you need a couple more minutes on this, give me a thumbs up in the Slack. And if not, please post your code, even if, if we come down to the wire and even if you haven't finished it, go ahead and post it. But if you want more time, give me a thumbs up in the Slack. Okay, I see a couple thumbs up in there. Let's just put 2 more minutes on here. All right, so it looks like maybe this function got a few of you caught up. I'm going to go ahead and walk through a solution. I'm going to code this a couple ways. I'm going to start off coding this probably in the simplest way, and that's just as the mean of a list, right? So this is some set of numeric values, and we can use the ones that are above. So A has all these values. So if we pass in, let's see, if we're passing in this list and we want to know what the mean is, it's just going to be the sum of the elements divided by the number of elements. And so that's as simple as the sum of the list divided by the length of the list, and we can return that. So at that point, I can just print the mean of A, and we should have a reasonable answer. So this is just the simplest version, simplest solution here. So 238.3, and we can see that could make sense. And notice we've got this, number 2000 here. 2000 is dragging our mean off to the right, isn't it? So we're getting something in the low 200s. Now, if I want to update this so that we can trim this out so that we lose the, say, 1 and the 2000, that's not too hard to do. I can say, I'll call this trim by, I'll set it to 0 and by default. And I'm going to add just a little more logic in here. So the first thing I'm going to do is I'm going to make a copy of the list. And the reason I'm doing that is that I might be modifying this list. And I don't want to modify something if we've passed it in general, right? There are times you might want to do that. we're going to settle on this paradigm of don't modify your parameter. And then I'm going to say, well, if trim by is greater than 0, then I'm going to sort this list, this copy of the list, right? And I'm going to remove the lower and upper number of items, right? So I'm going to go from, I can actually go from trim by up to negative trim by. And that should work. So we sort the list, and then we slice it from the lower value. So if this is 1, we're going to start at the second item. And if, if trim by is 1, we're going to stop before the final item. And something I want to point out here, if trim by is greater than 0, we could just say if trim by, because 0 is a false value. Anything aside from 0 will be a true value, but I'll leave it as that. Okay, so when I call this now, I'm going to trim by 1, okay? And let's see what we get. Oh, looks like we're still getting 238.3. Let's see, what am I missing here? I'm returning the list. And I should be returning list underscore. So that should work now. So 47.5, let's look at that in context here. 47.5 is somewhat more representative. It looks like it would sit right here, kind of between 35 and 67. But if we're looking at this data, 220 and 2000 sort of seem like they're taking up, they're still dragging everything to the right. And we might even want to trim by 2 here, right? We might want to do that. And if we do that, then it starts looking, the value we're getting out of this starts looking more representative of this if it's a sample. And I want to just, revisit this idea for just a second. If we are removing data, we need to have a good justification to do so, because there's a chance that 220 and 2000 are actually well representative of the data in question. And if we are removing representative data, then we're likely making a mistake. Okay, so a trimmed mean is fine. You want to err on the side of avoiding dropping data in general, but that's a much bigger discussion. So I'm going to paste this into the Slack so you have it, because we're going to have a couple things that are dependent on it today and in our next stats class. There's a question here: what does the underscore naming convention mean? So often we'll use an underscore in our naming to indicate that we've modified something, and some change is or has taken place, is taking place or has taken place. We could as soon call this list copy, right? That would be just as valid. I tend to just do list underscore if I'm making a copy of something, or dictionary underscore, or whatever it might be. But yeah, there are a few different naming conventions when it comes to that sort of thing. And this one's pretty common, just using an underscore. Is there a specific reason I use the sort function instead of the sort method? I like sorted. I tend to use sorted more than I use sort. Now, is there a good reason to do that? I think they're roughly equivalent, either way you are, well, if you're using sorted, you are destroying the original variable, and you're overriding it with this result. And so that's probably going to use up slightly more memory, but it'll be so negligible that unless you're doing something massively parallel even, you're not even going to notice. So yeah, this really is the equivalent of list dot sort, right? We could just do that, and then do the indexing of it. I prefer this personally. I think Python is nice in the way that you can destroy and recreate things. I think as long as you know what you're doing, it's fine either way. But they will be equivalent. There's no specifically good reason to use one over the other in this case. All right, so you've got that function. Now I'm going to have you apply the function in another breakout. So there are, I'm just going to put this up here, and I'll paste in the data, and then I'll read through this, and we can get a sense of what this challenge is about. And I can answer that next question really quick. Time complexity in terms of using the sum function versus a for loop, use the sum function. It's going to be it is going to be more efficient than using a for loop. In general, if there is a convenience function like sum or len or any of those, they will be better optimized, and you should get a much faster performance and potentially lower time complexity. Although in this case, I'm not. I think the time complexity should be lower still. Definitely, the time it takes to run will be lower. Okay, so I just put in the data here, and let's talk about what the ask is here. There's an article published in a journal called Indoor Air that compares endotoxin concentrations in urban households versus farmhouses. And I'm not sure what this scale is, but let's not worry too much about that. We're looking for the sample mean for each group, or the mean for each group, however you want to say that. And we've got urban versus farmhouse. And then you're going to not only get the sample mean, but get the trimmed mean where your trim by is set to 1, okay? Yeah, that's, I think that should be pretty straightforward. This is just applying the function, let's say the function that I just put in the Slack for you to use. So I'm going to set a timer for 4 minutes, and yeah, go for it. Okay. Are people having trouble getting to answers on this? Oh, no, I'm sorry. For some reason, Slack didn't click at me when everyone posted their answers. Awesome. Looks like a lot of you got there. Let's go through and just work through this solution. And I'm going to put in some, some stuff like rounding things, which I think it's generally good to round your answers. So I'll do a little bit of that while we're going. Okay, so we've got urban and farmhouse, and I just have the data here in Python lists. And the first thing we're going to look at is the mean of urban, right? And so the mean of this, I'll just point this out, is going to be 21.54545454. So much of this is not meaningful, okay? And when we're looking at this data, we've got measurements to one place, right? So we definitely don't want to include anything further than one place. And as a result, I'm going to just round this, and I'll round it to 1 decimal place. So 21.5, that seems reasonable. And I'm going to put like a nicer message on this, and I'm not saying that you have to do this in your answers, but if you do have time, it's nice to do this sort of thing. I'm going to use an F string. We're going to be doing a lot with F strings. I'm going to use them constantly. So this is the sample mean for urban, and that's the rounded mean for urban. Now, if I want to get the trimmed mean for urban, well, sorry, I'll do that in a second. Let's look at the sample mean for farmhouse, which I'll just change those. All right, and in the second part of this, I'm just going to print an empty line. We're going to do the trimmed sample mean for urban and the trimmed sample mean for farmhouse. And I can change mean here to be trim by, do trim by 1, and trim by 1 on the next one. And we should see something reasonable here, right? Sample mean urban, 21.5, sample mean farmhouse, 8.6. And when we see the trim sample mean for urban versus the trim sample mean for farmhouse, let me just point this out. Let's consider that there is a more dramatic reduction in the sample mean for urban than there is in the sample mean for farmhouse. Now, why is that? Likely because we have a strong outlier. And if you look at the urban data, we've got a couple much higher values that we see, like 33 and 80 and 35. So we're trimming out that 80. Again, if these are samples and, we want to think about, well, okay, we sampled what, like 12, 14 houses, urban houses here, urban spaces here. Now, is it really an outlier that we see 80, or does 80 occur more commonly? Do we actually want to trim that out? Does that make our mean more representative of the data? We need more information. And that is so often the case in any of these questions. We're like, well, which is better, the trimmed mean or the untrimmed mean? Well, we can't really answer that question without analyzing the problem more and analyzing the domain much more than we already have. Because for us, this is just a list of numbers, and we can't say that the trimmed mean is better or worse. We can operate on intuition, but it's better to operate on information. Okay, so that's what we'll cover for mean for right now. Let's talk about the median. So the two big measures of central tendency that we consider are the mean and the median. And they are, they aren't, we don't want to think about one as being better or worse than the other. And even when we're looking at some data, like if we have a list of data, we might ask a question like, which is more representative? Oh, sure, I can copy in that code block to Slack, 1 sec. I'm gonna leave those comments in, so we'll do that. Okay. All right, so one of the types of questions you'll see in stats books, and we're gonna have a couple of these questions here, are questions like, which is better on this data, the mean or the median? And you wanna be really careful about that kind of question because these are different measurements, right? Median is a different measurement from the mean. They're different. They're telling you different things. They're both measures of centrality, but they're different types of centrality, right? The mean, the centrality of the mean can get pulled one way or the other by extremes in the data. Are the extremes in the data meaningful or are they not? That becomes an important question when you're considering the mean. When you're considering the median, well, the median is just the middle value of the data. So let's think about a list of numbers. Oh, don't know why that happened. Oh, wow. Oh, okay. Well, that's fine. Let me just reopen that sketch program. By the way, there's a process on my computer that's using something like 90% of my CPU right now for some reason, and not really sure what's going on there, but could probably be solved with a restart. Hopefully I don't have to do that. Hopefully we can just keep going. Okay, so let's think about median. And in general, we're going to represent median with MED, or just the whole word median. And it'll be the median of some data set. Here we'll just consider A. We'll just keep using A. You might see from time to time this X tilde. We're not going to use that. And the reason being X bar and X tilde, if you see these in a paper somewhere, it's going to be really, I would see this and I would just assume it's X bar. So we're not going to use X tilde. Just pointing out that there are different symbols out there that people use. We'll use MED for median. Okay, so let's say we've got A, and A is 7, 1, 4, 5, and 12. The way that we're going to discover the median here is we're going to put these in order, right? And that's just going to be 1, 4, 5, 7, 12. The median is just going to be the middle value. Easy, right? So it's easy to do this by hand with 5 values. It's maybe a little trickier to do this procedurally in code, not that much trickier, but a little trickier. This is for an odd length list, right? This is for an odd length list. We just choose the middle value. What about for an even length list? Let's do the median of B, where B is, I don't know, 6, 12, 1, 9, 14, and 8. So again, we're going to reorder these. We're going to put them in order. So that's going to be 1, 6, 8, 9, 12, and 14. So what we're going to do for this is we're going to look at the 2 middle values. We're going to take the mean of the 2 middle values. That's it. Take the mean. It's the same thing as just adding them together, dividing by 2. 17 divided by 2 is 8.5. So notice that our median is not actually in the data. That's going to become more important later. Our median in this case is not represented in the data. So if we're going to talk the upper and lower parts of our data, if it's an even length list, those upper and lower parts are going to include all the values if we look at them together. Okay. So I think we're going to jump right into, well, you know what? Let's take a break. And when we come back, I'm going to have you code the median function. And yeah, we'll just do that. So I'm going to put a 6-minute break. I'll just put it on my little terminal timer here, and I'll see you all back here shortly. All right, let's jump back into it. So we have kind of a general simple algorithm that we can think about for calculating the median, and that is we sort the list, right? We find the middle value. If the list is odd, we just grab that middle value. That's the answer. If the list is even, then we take the mean of the two middle values, right? We just sum them and then divide by 2, or we can call the mean function that we wrote earlier. Either way is going to be fine. So we already, worked through a couple examples of those, and you know what? I'll leave that up there because I'm going to have you write. I'm going to have you write a mean function, and that even list and the odd list. I'll put that in the Slack because you should test your function, and you're going to code the median function. And we'll take 6 minutes on this, and we'll add a couple minutes if necessary. Again, this is a situation where if when we get down to time, whatever code you've written, please put it in the Slack. Okay, at the point where we I cut us off. So that. And for those of you who might need just a little more to work off of, I'm just going to put a little function header here. Feel free to copy this, the median of a list, and then you're going to write your code in this space, right? So I'll just put a pass there. You're going to replace the pass with your code. All right. So 6 minutes. Do your best to try to solve this, and however far you get, don't worry. We will code through this, and it's something that can be reviewed later. If you'd like 2 more minutes on this, 2 or let's say 3 more minutes on this, give me a thumbs up in the Slack. Okay. All right, so let's code this out. There's a little bit more complexity here than in the mean function. And yeah, so let's look at that. We're passing in a list, and I think it's important in general, right, to look at this in the context of some actual data. And I'll put that down here. And then I'll just get these started. So the median of the odd list, and then, well, that, and the median of the even list. This is a practice I like, just having something I can run really quick so that I don't write a whole bunch of code without running it. And yeah, so let's look at this in terms of this kind of loose algorithm that we have up here. If I can make that a little bit bigger. So the first thing we have here is we're going to sort the list. And I can call this list sorted. I can just call it list underscore as I did before. And that'll be the list that is now sorted. And the first thing I'm going to check is this odd? Well, a way that I can check that is if the length of the list mod 2. Now, the full expression would be, does that equal 1? If that evaluates to true, great. Then we perform, then we know that the list is odd and we perform whatever code is underneath this. But as I said before, 0 is considered false. Anything that's not 0 is considered true. So I can actually just abbreviate this to if length of list mod 2. And if that evaluates to 1, well, 1 is truthy, right? So I'm going to find the middle value of the odd length list. And actually, I'm going to find the middle index in this case. So this is going to be, I'll call this mid index, just to be very clear. This is going to be the length of the list divided by 2. And when we divide, that's going to give us a float. So I need to modify this to be an integer. So I'm just going to cast that to be an integer. And then I can return the, list sorted sub mid. So this is going to be the middle value, mid index. It's not list sorted, it's just list underscore. Okay, so that should work for this odd list. And oops, find the actual thing. There we go. Let's just see what we get. So we get 14 out of this. Now, is that correct? Do we know if that's correct? A nice way to do this is just to print the sorted version of the odd list. And probably just print it here. And we can look at it in context of that list. So 13, 13, 13, 13, 14, 14, 16, 18, 21. Okay, so if we just cross off the right and the left values here, 13 and 21, 13 and 18, 13 and 16, 13 and 14, we get 14. Is that the right 14? Well, if we really want to know, we can change this 14 to a 15 up here, and we should still get 14, and we do. Okay, so that odd list is working fine. The other condition, the other possible path we can take here in this control flow is an even length list. There's only 2 states, right? Odd or even with the length of these. So in this case, I'm going to copy this middle index code, but this is actually, for an even length list, this is going to be our upper middle index, okay? So I'm getting our upper middle index like so, and I'm going to return the mean of this and the index just below it, right? So I've got upper middle index and the upper middle, sorry, I've got the upper middle index and the index just below it. So that -1, upper middle index -1. So upper middle index -1 is going to be one of our values. And we're going to get that out of our sorted list. The other value is the one that we already, it's just that list upper middle index. I'm going to take both of these and I'm going to put them in a list. And I'm going to get the mean of that list. And, I'm just going to return it. So that should work. And I'm going to show you, I'm going to modify this a little bit in just a second and show you another way of thinking about it. Or another way to represent it. Logically, it's the same way. So notice here, if we get to these two middle values, 12 and 13, well, 12 plus 13 divided by 2 is just going to be 12.5, right? That makes sense. Of course, that median does not exist within the list itself because it is the value in between 12 and 13. All right. So we can simplify this code a little bit. Let me paste it in as is first, and I'll do that with everything here. And then I accidentally hit live share, and 20 pop-up messages later, VS Code is ready to work again. Okay, so let me simplify this. Notice I'm getting this mid-index value and putting it in here. Well, I can simplify this a little bit by just doing this directly, right? Logically, this is going to be the same thing. The other thing I can do is I can, if I don't want this to be, if I don't want this to be dependent on my prior mean function, I can add these two numbers together and just divide by 2. And that will be logically the same thing. Okay. If I really wanted to kind of take this to an extreme, I could cut this out, but I want you to notice that this is going to lead to slightly less readable code, right? Even if I have a shorter function, it's a little bit less readable. I could take this, I could take this further if I wanted to, but I think this, well, why don't I do that? I'm just going to take this a little bit further and show you that you can continually reduce a function in terms of how much code is there. And in the process of doing that, you lose some readability. So now I'm going to paste this in as well for, just as something that if you want to reference as an unreadable blob, then, but logically sound, it's here. Well, before I say it's logically sound, I should probably run it one more time and make sure I didn't introduce an error somewhere. Okay, works the same. Okay, so there's a question. Will I paste in the middle version before the unreadability? Oh, did I not do that? Oh my gosh. I copied it and then I didn't paste it in. So let me just do that. There we go. Yep. Let me make sure that runs. Yep, that's fine. Okay, yeah, so this is the actual readable version, which I meant to paste in with all of this. Yeah, so the interesting thing, there's a comment, it increases the amount of processing when we, let's see, yeah, try to redo this. Oh, you know what? I have this set to, the key command for redo I have set for something else. So it's interesting. We don't necessarily perform much more computationally because we throw the sort into here and we get rid of a little bit of memory overhead if we condense the code. But at the end of the day, it's not going to be significant either way. Computationally, it should be roughly equivalent. We could time it or something like that, but it's negligible. And I think at this stage, the computation cost and time complexity of a lot of these things we're not as concerned with. We'll start getting a little concerned with that when we get to sampling and counting, because there are going to be intractable problems in counting approaches that we can approach solutions with sampling approaches, and that is a time complexity problem. But when it comes to these kinds of functions, unless you have 20 nested loops that aren't really doing anything very helpful, these, those two versions of code will be equivalent, or equivalent enough. You might be just slightly off in the time cost of them. Okay. So let's look at a variation on that prior indoor air problem. And this should be pretty quick. It says 3 minutes on this. Let's do 4. And, make sure that, well, not make sure you do this, but try to round your answers. Although in this case, I'm sorry, you don't need to round in this case. It shouldn't matter. But, try to use an F string if you have a little bit of familiarity with F strings. If not, that's okay. Really, you're just going to be calculating the median of both of these. So let's put 4 minutes on and go ahead and do that. Okay, so let's look at this. This isn't really any more complex than, you know, a function call, right? So first thing we just need our data, our urban and farmhouse data. And even though we have it above, I'm just going to put it back in here. And see this in context, I think it's nice to print a sorted version of our lists. And I'll print sorted of urban, and then we're going to take the median of urban. In fact, it's not a bad idea at all. I'm gonna snag all of this, and the only thing I'm going to change, I'm going to print the sorted of urban, print the sorted of farmhouse, and then comment all of this, and one nice thing, Command D or Control D. No, I'll do it here first. So mean. Okay. And change all of these to median. And of course, we don't need, so sample median urban, sample median farmhouse. Oh, we don't need all of the rest of that, do we? Copy paste is your friend. You'll tend to make less errors. So let's run that. And let's look at these medians in context of the data. Right, so when we're looking at this, sample median for urban is 17. Of course, that's right there in the middle. Obviously, that looks very central. 8.9. Oh, interesting. I guess these are both, I think these are both odd length lists. So it's not really testing our evenness and oddness, which is fine. But I assumed it was for some reason. But yeah, pretty straightforward, pretty simple. Notice in this case, in the representation for the urban endotoxin levels, we are not affected by these more extreme values, right? We are not heavily affected by these, especially this one, right? This one that is more than double any of the other values. So that's a good thing to remember about median in general is, you know, it gives you a sense of centrality that is unaffected by extremes in the data. Okay, so let's do another, well, yeah, let's do, I'm going to do this breakout, okay? I'm going to walk us through it because I think there's, I think it's pretty straightforward, and we've already done these essentially. So let's just look at it because it's a good sort of textbook problem. An issue of a recent magazine reported the following home sale amounts for a sample of homes in Alameda, all of which were sold in the previous month. Okay, so this is in 1 month, 590, 615, blah, 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 blah. Notice there's this 1285 in here. That looks pretty high. Oh, sure. Let me paste that code. My apologies. Let me just snag this. Right there. Yeah, thanks for reminding me. Sometimes I forget to paste code. Okay. All right, so we've got these sale amounts, and these are in thousands. So this one is 1.3 million, roughly. This one's 679,000, so on. Find the mean value of the homes, find the median value of the homes. Do I think the mean or median is better? Sorry, I thought I pasted this in. Let me paste it in just in case I didn't. Okay. So solving this is pretty easy. Well, it's easy in the sense of we're just going to take these numbers and we've got home sales, and I'm going to make this a list. Currently, if you see those curly braces, that would be a set, but set or list, it shouldn't matter here. Either way will work. So I can print an F string. Let's see, mean of home sales. And this is just going to be mean of home sales, right? And it's a good practice, just to round things. And I'm going to round this to a whole number. And the next thing we want to consider is the median. And that's easy enough. And then there's this question, do I think the median or median, the mean or median is a better measure of center for this data? And we're going to think about that, okay? If you have thoughts on that, well, let's look at this. The mean of the home sales is 620. The median of the home sales is 582. And I think it's often helpful. Again, I'll just print the sorted version of the home sales just to see it. Okay, so what do you think is better here, the mean or the median, if you have a strong argument? And remember, this is for April, and let's assume it's a sample. I think, thinking of it as a sample is more appropriate. Which do you think is better, the mean or the median? And yeah, just take a couple minutes and yeah, put your thoughts into the Slack. So I'll just keep an eye on the clock, and we'll aim for about 2 minutes. And justify your answer as well, please. Okay, so let's, there are a lot of calls for median, and I think we can make a strong argument for that. in terms of the median being more central, right? Like the median is sitting right in there, and that's fair. And so our median is there, our mean is up here, right? Now, here's the thing. This is the sales for 1 month in April. And we want to think about this in context of the problem, right? Is 1.2 million, 1.3 million an outlier, right? Is that an outlier? Or is that representative of an occurrence in this phenomenon of home sales? There's a good chance, I believe that there's a good chance that, that 1.3 million is something that's going to come around. Like there are going to be values that come around like that, maybe every month, maybe there's 2 a month, maybe there's 1 every couple months, something like that. That appearance, the appearance of that value is going to occur. And so even if our X bar is all the way out to the right, X bar might be more representative of the phenomenon itself. In terms of centrality, though, median obviously is more central in our data. Why is it more central? Well, for reasons that we said above, median is what we call resistant to outliers. That's one of the strong cases for it. Now, does that mean it's more representative of the data? Not necessarily. But yeah, so we're going to think about mean and median as being very different things. They're helpful for different reasons. And I think often they're pitted in a competition, like which is better, but neither are better. They both describe different aspects. They're different moments of our data, right? They're different views, perspectives on our data. Awesome. Okay, so, I'm just going to repeat it one more time. The mean is not resistant to outliers. If we have an extreme value on the right or the left, that's going to drag our mean from one side or to the other side. The median is resistant to outliers, obviously, because we don't care about everything else. We just care about that middle value when we're considering the median. So let's think about one last measure of centrality. We might get into a little bit of sampling after this if there's time, but we might push that to next class. So there's this concept of the mode, and the mode is a different perspective. It's a different moment, right? That we can consider. Let's say we have non-numeric data, and I think it's easy to think about mode through the context of non-numeric data. And why don't I do this in a text editor? I think it'll make more sense. Okay, so let's say we have some pets. We have a cat, and we have a dog, and we have a goldfish, and ferret, and let's say maybe we have 2 ferrets, and maybe we have 3 cats. Mode is going to just be the most frequent item. The mode is the most frequent item. In this case, we have a first mode, which is a cat. We have a second mode, which is a ferret. And notice here, we've got this kind of data that is, it's categorical, right? It's just the names of things. And what we might wonder is, well, how do you get the median of these pets? Well, I don't think we're going to throw them into a blender and then portion out, some amount of it. Like that doesn't make sense. That's going to be a grotesque scene. We can't really get the median because there's nothing middle about this, right? Unless we arrange them by size, right? Well, then we would think goldfish, ferret, cat, dog, maybe, and maybe ferret would be the median, but that doesn't make sense. That's not a helpful way to think about this. It turns out that mode is an extremely helpful thing. And one of the ways that it's helpful is through the idea of histograms, right? Where we can establish bins, right? So let's say we're talking, let's make bins that represent ranges of heights of trees in a forest, something like that. And maybe this is 10 meters, maybe this is 25 meters out here. And let's imagine, so in this case, if we're looking at this, we might have, let's say this is 10 to 13 meters, and then this next one would be 13 to, let's say, 16 meters, and so on. Let's just imagine that we've got some range of continuous outcomes that we throw into bins, right? So it turns out that our modal, our most likely occurrence, if we go in and pull something from random, is going to be something in this 10 to 13 range. So, the other thing to consider is that our mean for this data, our X bar, might not be in that 10 to 13 range, given the way this frequency works out, right? We might have a number of other shapes of data that look like, where, if we're going to if this is numeric values packed into these bins or these buckets, right, we might see an X bar that's over here or something like that, whereas our mode is actually more representative of the data that we are considering. So, mode can apply to numeric data as well. And in those cases, it's going to be the most likely value, the most common value if you were to select values at random, or the most common range of values if we're considering this in terms of bucketed values. We'll get into something like that a little bit further on. But I want to just code through a simple mode function. And in this function, I want to introduce kind of an idea. This is a common sort of algorithm form, simple algorithm form. And there's a method in here that you may not have seen yet that I want to show you. So here are our pets, and we'll just continue with this idea that there's these pets and we're considering modes from the pets. If I want to count how many ferrets there are, I can do it like this, right? Very simple method. Count of the item ferret in pets. That's all that is. And so this is going to facilitate a mode function, a very simple mode function. And I don't want to claim that this is the best mode function that you could ever write. There are better functions, but this is going to be a good template for other types of problems that you're going to encounter. There's a question in the odd-shaped diagram of bins, would I first sort the bins by size? Let's just visit that question really quickly. So let's say, we've got these bins, and let's say that these represent ranges, numeric ranges. And there's some function underlying this, and maybe I'll just keep this simple and say this is 0 to 10, this is slightly more than 10 to 20, and so on, right? Obviously, our most common outcome is going to be this. We have more values there than in any of these other bins, but so in this case, I don't think I would personally sort this. What I would do is, take all my samples, put them into bins, count how many are in each bin, and just consider the modal range in this case to be, this is 21 to 30, 31 to 40. It would be in this, slightly more than 40 to 50 range would be our modal bin. Notice this is arbitrary as well. Like, is there not a good reason to do 35 to 55 instead. You know, like we define the ranges of these histograms and these bins. And so we influence the modes as a result. I think it's more helpful to look at this in the range from 0 up to, you know, in order of the actual numeric components that fill those buckets. But we'll get into something that looks more like that later on when we get into, you know, kind of defining our own phenomena. Okay, so obviously ferret in this is not the mode. Cat is the mode. We can see that by looking at it. But what if we had hundreds and hundreds of cats and ferrets and goldfish, things like that? You know, like maybe multiply this by 5. And, you know, so now we've got many more ferrets and many more cats, right? We've got 15 cats and 10 ferrets after I multiply that by 5. So we've got this count function, and I think that's going to be instrumental in a simple approach to solving this kind of problem, okay? So I'm going to write a function called mode. Maybe I'll give us a little bit more space to look at this. And we're passing in a list. Our goal is to return the most frequent item. And we're going to ignore an equally frequent item, you know, whatever the first most frequent item is going to be, that's what we're going to go with. And we're going to ignore the second mode, which would be the second most frequent item. This is a very simple function. So I'm going to make an assumption first that there's a most occurring item in the first position. And in this case, maybe I'll put also some other pet, hermit crab. Okay, so hermit crab should not be the mode, but we're going to make an assumption in this function that it is. And then I'm going to look at every other item, and we're going to make a decision, is the next item we're looking at more frequent than the item that we currently think is the most occurring? So for each item in our list, and I don't need to look at everything, I can look at everything from the next item, right, list sub 1 until the end, which is what this slice is doing here. And I can say if the count of that item is greater than the count of the one that we are assuming is most occurring, then we can update our most occurring item. Like so. Again, the reason I'm not saying that this is the best mode function or anything like that. The reason I'm writing this like this is to illustrate a pattern. This is a common algorithmic pattern where we make an assumption, we take a guess, right? We take a guess, and then we make a series of observations and we update that guess. So, you know, ultimately, we end up with a result. So what is the mode of our pets? I think, you know, it shouldn't be too surprising what that answer is when I run this. It's a cat. Makes sense. Now, what happens, I think I mentioned this, what happens if we have an equal number of cats and ferrets? Then you know, which of these is going to show up as being the most common? It's still going to be a cat. Now, notice that this function is broken in this way, right? It's giving us, if we've got something that is bimodal, right, where there are two modes, it's giving us the first mode that it discovered. So you might want to think about how would you rewrite this function so that you get both modes? How would you rewrite this function so you get a first mode and a second mode, right? There are a lot of different approaches. And also, why are we getting cat instead of ferret here? Well, it's that if we count ferret and it's not, it doesn't satisfy this condition of being greater than, it has to be explicitly greater than, not greater than or equal to, then it's going to end up being cat. Now, if I change this to greater than or equal to, I don't think it should be too surprising. Oh, actually, if the list.count of the item is greater than, oh, it's still going to be cat because cat is the last item. However, if we switch this around and we make ferret the last item, I think, we're going to see ferret. So whatever the final thing that it sees that is equally frequent would be the result. So that's just simply changing this greater than for greater than or equals. I'm going to change this back to a greater than, and I'll go ahead and throw this code into the Slack. Okay. What would you do if you have 3 or 4 modes? Yeah, that's an issue. You'd probably use a different algorithm, to be honest. I think that's the thing to consider, that I'm showing this as a very simple approach, right? But there are more complex ways of solving the problem of the mode. And one way you could do that is you could make a counts dictionary, right? Where, for example, you have the item, and paired with the item, you have the count of that item. I don't think y'all have gotten too deep into dictionaries yet. That's going to be something over the next few days with Clark. So I'm going to leave that for now, and we can likely come back and solve a more complex mode, like a better mode function at that time. But for now, this pattern this pattern is something that occurs a lot, right? You take a guess and then you update your guess based on your observations. Awesome. Yeah. So next time we'll look at some sampling. Just a quick example of sampling, and we'll talk continuous versus discrete, and then we'll move into the second part of these basic stats, right, where we're talking about measures of spread. So this is measures of centrality, and then the next logical thing that we'll consider is measures of spread. Cool. That's class for today. Feel free to sign off. I'll stay on for questions. I think I'm also going to stay on for a bit and meet with a student on some specific questions, sort of at the end of that. Feel free to come off mute if if you like. I'll go ahead and stop the recording.